Makes sense. Right, I need to do this. Sorry, we'll get there eventually. Or perhaps we won't. Okay, very good. We're there eventually. Okay, so I'm Ed. I probably met most of you yesterday, but from the University of Surrey. And sort of in line with what Jeff said this morning about overlap functions, we want to sort of touch on how reactions in general are going to interface with structure. So the idea of this talk is to say something a little bit about shell model calculations and give a very sort of brief overview of the theory that goes into shell model. And it's not going to be very in-depth, I'm afraid, but give a brief overview and then talk about some of the more kind of practical aspects of doing shell model calculations. So even if you don't have to do any shell model calculations for the projects that you do at the end of the course, you may well in the future need to do shell model calculations, and it's very useful to have an idea of the sort of structure input that goes into them because it's the sort of structure that you'll be probing with reactions if you're doing experiments or doing reaction theory. So is this does this need a switch on or anything? Anybody know? Ah, okay, wonderful. Okay, so seems clear a bit. So I'm going to start by giving a brief overview of the shell model. It's not going to be very in-depth, I say, but I mean, I'll point to some specific references to start with, which will give you some useful guides if you want to go away and learn a bit more about actually what goes into the calculations in detail, and the idea of central potentials and residual interactions and the general procedures for doing a sort of calculation. And then I'll talk about some examples of calculations. So in the example session today, we've set up new shell X, which is a modern shell model code on one of the Windows servers here, and hopefully we'll be able to get you guys running some calculations. It may or may not fall to pieces because the computer isn't enormous, and having 15 people trying to do it all at the same time might cause problems, but we'll give it a go. So there's a tutorial later, and we'll get to that later. So I'm going to give you some idea, look at some of the details of the outputs of the calculation so you can understand what you'd expect to see and what the sort of level of detail you can expect to get from a shell model calculation is. And what's really useful to you when you're looking at reactions experiments. And then a bit of a sort of practical field guide to doing shell model calculations, what you need to think about when you're thinking about which interactions and model spaces to use, how those model spaces might be truncated, and whether those truncations are appropriate to the interactions that you're going to use, and some pitfalls that I've sort of picked up and fallen into myself along the years of doing these sorts of calculations. And then just a brief overview of the code that we're actually going to use. And as I say, the tutorial is going to cover this example that Jeff showed earlier. Proton spectroscopic factors for neon-26 are appropriate for a knockout reaction, removing a proton, or maybe a dihelium-3 proton pickup reaction. Okay, so a brief overview of the shell model. This is the shell model theory part. So first, these references. There are much better people at me that explain the shell model, really, and I'd point you to these two sets of lecture notes from the Euro School. Actually, this should be volume 3, I think, rather than volume 2, or rather, no, that's right, actually, that's right. So it's volume 1 and 2. So you can get these on the web. They're hyperlinked in the PowerPoint, so you can go to the Euro School website, and there are big bundles of all the lecture notes from these two schools. And in there are these two articles which give a relatively gentle introduction to the shell model, which is actually reasonably tricky to find. There are lots and lots of good sets of notes and textbooks on the shell model, but they often dive in at quite a deep level to start with. So these two articles in particular are good at explaining sort of the basic ideas behind the shell model. If you want to take a look at those are the ones I'd recommend to start with. But there are lots of other good textbooks. So the idea is this. I mean, a nucleus, if we're thinking of it as sort of a bag of nucleons, is a whole sum of different two-body interactions, right? We don't really have a mean field potential. But if you take a nucleon in the middle of a nucleus and it feels the sort of short-range interactions by the nuclei, the nucleons that are also in the middle. So somehow the degree of interaction and the potential that's felt by the nucleons in the middle of a nucleus is somehow dependent on the density. And as you go further to the edge of a nucleus, that interactions, there'll be fewer and fewer interactions in the immediate volume about the nucleon that you're actually interested in, and this potential will decrease to zero as you get outside the nucleus itself. So we have this sort of general idea that from a whole series of two-body interactions with all the different nucleons in the nucleus, you get this idea of a sort of mean field type potential that's deepest in the middle of a nucleus and gradually falls to zero as you move outwards. And that's sort of, in essence, the initial idea behind the shell model. What we have is a Hamiltonian that has a kinetic part and a potential part that's the sum of all the kinetic energies for each of the individual nucleons and a sum of all the different two-body interactions between different pairs of nucleons. And as you imagine, if you get to 50 or 60 nucleons, suddenly you have a very large number of two-body interactions. But the idea is what we can do is assume that all these two-body interactions are essentially can be approximated by a central potential, a mean field, as it were. And you can add to this a mean field to the kinetic part, essentially, and then subtract this mean field over here on the right. And what you're then left with is this bit, which is a sort of one-body central potential, where the nucleons are sort of sitting in something like a Wood-Saxon potential, and some residual part that's effectively the sum of all these two-body interactions minus this central potential. And the idea is that this thing is rather smaller than the central part. And so what essentially this is doing is splitting our Hamiltonian into a central potential and a residual two-body interaction that takes account of the fact that there are all these interactions between different pairs of nucleons, but that effect is rather smaller than the central part that you've just taken out. So this is the starting point. And what we want to do is find the eigenvalues and eigenstates of this Hamiltonian. I'm denoting those here psi alpha. And so we want to find the energy, so we can find the energy spectrum of nuclei, whichever nucleus that we happen to be interested in. And then maybe we want to do something else with these. We want to overlap with other states and other nuclei to find spectroscopic factors, or two nucleon amplitudes, say. Or maybe B of GT, so we want to find interested in beta decay rates or things like that. So what we want to do is solve for these energies and these eigenvalues, and then we can use the states to calculate things that we're actually interested in. And the starting point is to take the solutions of the central part of the potential, which are essentially just Slater determinants or products of different single particle wave functions. So this is our central part of the potential that just contains the kinetic and that sort of central potential term. And these will have energy eigenvalues and these states phi alpha, which say are essentially just antisymmetrized products of single nucleon wave functions. And to solve the full Hamiltonian, we need matrix elements of all of these solutions of the central potential, which we can then diagonalize. Okay? So the matrix element of the central potential part can be calculated using some assumed potential that you're assuming for that mean field form, or using single particle energies for each of the single particle orbits that each of the individual nucleons are existing in. So one of the crucial things in the shell model is that any n-particle shell model matrix element can be reduced to a linear combination of two-particle matrix elements. So the things that we're going to want to calculate, or the things that are going to parameterize our interaction effectively, are these matrix elements between these very complicated products of single particle states. So these are two different single particle Slater determinant states, and we have our residual interaction H12, which was the bit that wasn't the central potential. And these involve however many nucleons are in the nucleus that you're actually interested in. So there are lots of individual nucleons here. But the whole point is that, and I'm not going to go into the details here, but those references that I pointed to you at the start will tell you more. These sorts of matrix elements can be reduced to sums over matrix elements involving just pairs of two nucleons, okay? So in the notation here, this is a matrix element of our residual interaction for our nucleons in state I and J, and their total angular momentum coupled to J and total isospin T, with nucleons in states K and L with the same total angular momentum and isospin. Okay, so and there is some coefficient here, and these are related to parentage coefficients that Jeff was talking about earlier in a slightly different way to he was using them. But the point here is that we're interested in this complex interaction, complicated interaction between our residual two-body interaction and these complicated states, and that can be just reduced to a sum of matrix elements between pairs of two particles. Okay, and this is how you end up specifying the interaction, your residual interaction, in terms of these two-body matrix elements between different pairs of single nucleons. And then the idea is, there's something cut off here actually, but so that may prove a problem later. But anyway, the idea is once you've worked out all these matrix elements between our basis states for the full Hamiltonian, we can diagonalize it, and then we get the energy eigenvalues for all the states of the nucleus that we're interested in, and we have the eigenvectors, so we can then process them and use them to calculate overlaps and so on. So this is very schematic, and I'm not going into any great detail because it's not really my expertise, but once we've done that, so we can obtain our solutions to this eigenvalue equation for the states of interest with their energies, and these states are written in terms of a sum over all these different basis states, and each of these is a different slated determinant of all those nucleons that are in the nucleus, and those slated determinants are putting different particles in different orbitals. Okay, so these are just different combinations, effectively, of putting the nucleons that you've got in your model space into different single particle states. And these amplitudes will come out of that diagonalization procedure. And once we've got these, we can do things like calculate spectroscopic factors. So this is what Jeff was talking about earlier. If we have a state that involves A nucleons, and this has some additional label omega, and it has a total angular momentum J, and we have another state psi A minus 1, so for A minus 1 nucleons, it has a different label and a different angular momentum. Our spectroscopic factor, defined in a shell model type way, is written like this. So this is a sort of called a reduced matrix element, which means it doesn't depend on the projections of these angular momentum. And this thing in here is a creation operator. So what this says is that if we add a nucleon to this state of A minus 1 nucleons, what is its overlap with our A body state? Okay, and so if this is our neon 26 state that we'll be looking at later, what is the sort of parentage of a particular fluorine 25 state plus a nucleon in state K? So this K label just is NLJ. It's just the quantum numbers of the nucleon that you're adding to this fluorine 25 state. And in this sort of shell model notation, this is what we'd call a spectroscopic factor. It's a matrix element of this creation operator. So once you've got these states, you can work these things out pretty easily. And the shell model codes that we're going to use later will allow you to do this pretty simply. And there are very similar expressions for, say, two nucleon overlaps. All that changes is the fact that this would be A minus 2, so it's an A minus 2 body state, and our operator in the middle changes. So instead of having a single nucleon creation operator, you have so it's got to be an antisymmetrized combination of two of these things to give you an antisymmetrized two nucleon state. So you're saying what's the parentage of a particular antisymmetrized two nucleon state in our A minus 2 body thing. And similarly, you can have similar different operators for beta decay for B of GTs, or from internal transitions, so where you're adding a nucleon into a single particle state and then removing it from a different state for a gamma decay, say. So this sort of thing is quite general. What happens is just the operator changes and maybe the particular states will change as well. But this is a spectroscopic factor that we'll calculate later. So this generalized procedure for doing a shell model calculation in terms of the algorithm, essentially, is given in this nice paper by McGregory. So the idea is that you choose and define what you have for your central potential H0, and then calculate the one particle eigenstates of this potential H0 in the desired model space, and we'll get onto model spaces later. And then the idea is to construct multi-nucleon eigenstates from of H0 from these one particle eigenstates. So this is creating your slated determinant states, and then specify the residual interaction. And as I said, this residual interaction can in general be specified by just looking at two-body matrix elements, so interactions of different pairs of nucleons. And then evaluate the matrix elements of this residual interaction between these multi-nucleon eigenstates that you earlier constructed, and by diagonalizing, calculate the eigenvectors and eigenvalues of this matrix. And that's, I mean, these steps are individually actually, well, so the first three steps are not too complicated, but it gradually gets progressively trickier. And in terms of computation time, a lot of time is spent in this last diagonalization procedure, because even in a relatively small model space, you can have hundreds and thousands of possible combinations of arranging your particles and their angular momentum couplings, and that leads to lots of states. Okay, so it's this diagonalization procedure, when this dimension of this is hundreds of thousands or millions, that takes the long time in a shell model calculation, and all of these steps are sort of technical, and I'm not going to go into the details here, but you know there are lots of places to look up the details. So there are different sorts of, well, basically all shell model codes do the same sort of thing, but they sometimes do it in slightly different ways. So there are different ways of constructing the multi-nucleon basis states. So there's something called the M scheme, which constructs the basis states on the basis of having each nucleon's projection Jz. So if you have a particular orbital, you specify that in terms of all the different projections of the angular momentum of that orbital, and then do that for each of the states, each of the orbitals within your model space. And this has some advantage in that you can describe those basis states very easily in terms of a binary number. So it's just ones and zeros for the occupancy of these states. And there are more complicated things, JJ coupling, so you construct states of particular angular momentum, and this involves coefficients of fractional parentage. These ways of expanding particular Jn, so n nucleons in state J, into a part that's got n minus 1 nucleons and a part that's got just 1 nucleon. So there are various technical ways of doing these sorts of things. The codes that I've got experience with, Oxbash, NuShell, and NuShell X, which are various generations of the same family that I'll talk about later, use both the M scheme and this JJ coupling. So the other thing is NuShell X, which is the code we'll use later, is PN formalism. So what this means is that it treats the protons and neutrons entirely separately. So when we're talking about isospin, really what we're saying is that on some level, protons and neutrons are the same thing, but they've just got a different isospin projection. PN formalism allows you to treat you treat your protons and neutrons entirely separately, which makes some of the computational things a bit easier. So the diagonalization is quicker because you're treating the states of protons and neutrons entirely separately. But it means that certainly in terms of the heritage of interactions that have been generated over the years, you need to be quite careful about the sort of truncations that you might use, because you can't do quite the same truncations in PM formalism that you can do in isospin formalism. But I'll come on to that again later. And different procedures in general are available for the diagonalization, which is the most computationally intensive part. But usually this Langsdale's algorithm is used, which quite efficiently finds the lowest energy eigenvalues. Although the more eigenvalues that you want to find, the longer and longer the process will take. Okay, so that's my very brief overview of shell model theory. Those references at the start are a very good place to start if you want to learn a bit more in depth. But really, I'm going to sort of get on to the practical aspects of shell model calculations and how they'll interface with what you're doing with reaction theory, and what information it's useful to take out of the shell model calculations, and some of the pitfalls that you'll get into eventually. So I'm going to look at some examples here. These are just trying to show you the output that you'll get from the shell model calculations and what bits and pieces are of interest and what you can learn from them. So the main thing that I'm going to talk about is this example of protons in neon 26 and the spectroscopic factors that Jeff had showed earlier. So when you do a shell model calculation, this is the sort of thing, I'll get on to how you actually do it later, but this is the sort of thing that you'll get out. So this is just an SD shell model space using USD interaction, which is a standard, stands for universal SD. It's just a good interaction for the whole of the SD shell space. So the SD is everything between oxygen 16 up to calcium 40. And what you get out when you do the calculation in terms of the levels, so you get a file that ends in .lpt, and it's got all this information here on the left, and you'll get a level scheme also as a PostScript file on the right. But what this shows basically is the excitation energy in the nucleus that you're interested in, progressing upwards gradually, the spin of a state and their parity, and this column here just highlights where the Arras states are. So these are the states have an entry in this column if they're the lowest spin of that state, essentially. And so this is useful for just getting an overview of how well your calculation is doing in terms of its agreement with experiment. What's handy is that the NuShellX produces this plot which shows you the theoretical calculations on the right. So these are the levels that are calculated for neon 26. So there's a 0 plus and there's a 2 plus that comes in about 2 MeV. And the 4 plus. The Arras states are labeled, but the other states aren't. I think the length of this line indicates essentially what spin they are. But, and on the left is the known experimental information, and usually this is a little bit out of date. So you can look up online whether there are more states to compare with in your particular nucleus. But in general, for this case at least, it does rather well actually, and that's not unexpected. In the USD, in the SD shell is not such a big space, and the interactions tend to be rather good. So what we want to look at now is the details of one of the wave functions. So you see at the end here, there's this string of, this is basically a file name here, and it ends in .lpe. So when you're using NuShellX, files that end in .lpe contain information about the levels, and they go into some detail about how the levels are decomposed in terms of which single particle orbits all the nucleons are sitting in, and their angular momentum couplings. And I'll show you those in a second. It's got a funny sort of file name, and the tutorial that I'll show you, that I'll give you later, has details about what these letters mean. Essentially, from right to left, you've got six letters, and this is true for any model space that you use, or any interaction, any nucleus you could calculate at all with NuShellX has these 6 letters, and what these indicate are the model space and the interaction, and then the number of valence protons, which is 2, because it's neon 26, which is 2 protons above oxygen 16, 2 protons above oxygen at least. A indicates the total number of valence particles, so A is actually represents 10. So the numbering system runs from 0 to 9, and then above 9 it starts using letters, because in principle you can have a large number of valence particles and it would screw up the file naming at least. But again, there's details in the tutorial about that. And then these just indicate the parity and the spin. Okay, so each of these is different. So if we look at this state here, say, it's basically the same as all the others, apart from this one has 6, which is 2 times the spin. So, and you'll get lots of different sorts of files that are all named in a very similar way. So the spectroscopic factors and 2 nucleon amplitudes, and any overlaps that you calculate will be named in a similar way. I'm going to talk a bit about the details that you get in those LPE files in terms of the details of the states. But I just want to sort of touch on and relate this to what Jeff was saying earlier in terms of his independent particle model. in the shell model, things are a lot more complicated than in the independent particle model because you can have all sorts of different configurations and they're mixed by the residual interaction. So if we were to think of neon-26 and just the protons in neon-26 in the simplest way, our simplest naive sort of picture of neon-26 would be that we have an oxygen-16 core and then we have 3 SD shell orbits. There's a D5 half, S a half, and D3 halves. And these are somehow, the energies between these are specified in the interaction in some way. And these may not be right. I mean, I've just drawn it schematically. And the energies between these can change and they depend on the interaction. But our simplest picture is that D5 halves is the lowest orbit above oxygen-16. And in the independent particle model, we might say that our nucleus, our neon-26 nucleus just has 2 protons in the D5 halves, and they just sit there, and that's the lowest energy configuration. And that might indeed be the case, so we'll see in a minute that this configuration probably does occur in neon-26, and maybe it's quite important. But obviously we can have other configurations. So instead of putting those 2 protons in D5 halves, we could put them in S a half, or if we wanted to, we could put them in D3 halves, okay? And all of these configurations is, so what we call these in terms of the shell model picture are partitions. Okay, so a partition is one way of putting nucleons in orbitals. Okay, so this is a particular partition, and I'll show you the details later. This is one particular partition. This is a partition. This is a partition, and these are just 3 possible partitions, 3 different ways of putting those 2 protons in those 3 single particle states. And in general, these will all mix. We might expect this one to be dominant because that D5 halves single particle state is lowest, but they will mix, and you'll get amplitudes for this sort of configuration and this sort of configuration in the ground state of neon-26. So the added complication is that there are different ways of angular momentum coupling these as well. So the partition is just how you put them in the orbits. But in addition, there are different ways of coupling these. So if we put 2 protons in D5 halves, the way of coupling all our, the angular momentum that we can couple all our protons to is either 0, 2, or 4. So you only get the even ones here because these 2 protons are in the same orbit and can obey the Pauli principle. But in principle, in addition to this sort of partition where the 2 nucleons are in the same orbit, we could have a partition where we put 1 proton in D5 halves and 1 proton in S a half. And the total angular momentum couplings for the 2 protons in these states are J equals 2 or 3. Okay, so I guess the idea I'm trying to get across is that when you're going beyond the independent particle model, things get complicated pretty quickly. So this is just 2 protons in the SD shell. We've already got, so we had 3 different partitions on the previous slide. We've got another one here. We could also put 1 in D5 halves and 1 in S half, and 1 in D5 halves and D3 halves. So there are 6 different partitions that you can have in the ground state of neon-26 just for the protons. And each of those has different angular momentum couplings. Okay? So the states that you're going to have when you do the diagonalization of the full wave function tend to get quite complicated. But the nice thing is NuShellX will give you all the detail of the states, and we'll show that, see that on the next slide. And of course, this is just protons. So in addition to all these partitions for protons, you have partitions for all the neutrons. And the neutrons, each of the neutron partitions can have different angular momentum couplings. And then you have to couple the angular momentum of the neutrons to the angular momentum of the protons to get the angular momentum of the full state. So coming from an independent particle model picture, things are more complicated and arguably a bit messy. But that's what you're dealing with, and the residual interaction is going to mix all these things together. So now I just want to show you what comes out in terms of these LPE files. So this is the level information for 0+ states in neon-26. Okay, so we've got 0, 0 at the end here, which is positive parity and total angular momentum 0. Okay, so this is just the first section of it. So you have this header information, which has been cut off, unfortunately. But this lists essentially what the calculation did. So there's the name of the model space and interaction up here, so you can look it up later, and some credits here, and details of the total angular momentum of this set of states and the ISA spin, which I'm not really sure why that's there, because this is a PN model calculation, but anyway. So the next thing that's listed after this lot are these partitions, okay? So this is the list of partitions that's possible in this calculation for Neon 26. And you see that you have two sets. So in this case, type A nucleons are neutrons and type B are protons. And first you have this list of all the partitions for type A, which is the neutrons, and then the list for protons. And we'll look at the protons first, because that's what we looked at just before. So again, we have 6 partitions. So these aren't labeled. Hopefully these aren't well labeled here. But what this means is this is the number of nucleons in each single particle state. Okay, and these first 3 are for protons, and the second 3 are for neutrons. Okay, so for our proton partitions, there's nothing in these last 3 states, so we can just ignore those. Okay, and for the protons, we have up to 2 in each of these single particle states, and the order of these is the same as the interaction file. So what in this case, this happens to be I think D3 halves, D5 halves, and S a half, and the order of those is specified right at the bottom of this file, but it's not here, and it's consistent with the interaction that goes into the calculation. So you can always check it there if you need to. And also, it's certainly in the neutron partitions, you can see it easily because this column has a maximum of 6 nucleons in it, which means it must be D5 halves. This one has a maximum of 4, which means it will be the D3 halves, and this one 2, which is S a half. But obviously that depends on the number of valence nucleons, so you can't really use that here because there's only 2 protons. But anyway, so what we have is a list of partitions. So our first partition, partition number 1, has 2 protons in D3 halves. And then partition number 2 has 1 in D3 halves and 1 in D5 halves. Partition number 3 has none in D3 halves, 2 in D5 halves, none in S a half. Right? So this is what we thought would be the lowest energy configuration, this partition number 3 for B, or for protons. And it goes on. Okay, so this just lists all the possible partitions for the nucleus that you're calculating for, and same for the neutrons. And there's a lot more for the neutrons because there are more neutrons there. So Neon 26 has, how many valence nucleons? Has 8 valence nucleons. So our core in this case for the SD shell space is oxygen 16. There are 10 valence nucleons in total, which is this A. 2 of them are protons, and the other 8 are neutrons. So this just lists the 12 different ways of distributing those 8 neutrons over the 3 single particle orbits that are involved. And so there's a number of different ways of doing it. Okay, so what these LPE files list after this is the decomposition of each state in terms of these partitions. So this is just the decomposition for the first state. So this says state number 1, and this is its binding energy. And if we flip back to the LPE files, we'll see that this first 0 plus state has a binding energy of 81.625 MeV, and here we have that same 81.625. So this state number 1 is the first 0 plus state in Neon 26. The first thing it gives you are the average numbers of nucleons in each orbit. Okay, so this is type A, so this is for neutrons, and what this says is that for this first 0 plus state in Neon 26, on average, if you average over that whole wave function, there are 0.72 neutrons in D3 halves, 5.66 in D5 halves, and 1.6 in S a half. So we should maybe touch base with what we might expect from a simple independent particle model. Okay, so if our independent particle model says the D5 halves is the lowest energy state, and then the S a half, and then the D3 halves, we might expect that our simplest lowest energy configuration would have 6 particles in 6 neutrons in D5 halves, 2 in S a half, and none in D3 halves. That's when we might simply naively expect to put our nucleons, and we're not so far off from that. So if we've got 5.6 in D5 halves, it's nearly full, okay, and 1.6 in S a half, so that's reasonably full as well, and then just a smaller amount in D3 halves. So you see that this is it's obviously more complicated, the independent particle model, but somewhere in here there is something of that sort of level of simplicity going on, that the nucleons will tend to fill the lowest energy single particle states, and then they'll get mixed a bit by the residual interaction. Okay, and then we have type B nucleons, which in this case are the protons. And again, so we've got 1.6 in the d5 halves, which is getting on for 2 roughly, which would be our independent particle model picture, and then some scraps in d3 halves and s a half. Okay, so that's the sort of simple bit. What happens next is a bit more complicated. So what this then decomposes is our wave function in terms of all the partitions that are involved and all their angular momentum couplings. So what this first line says is if we have the total angular momentum of our A nucleons, which are the neutrons, so the total angular momentum of the A neutrons, the total angular momentum of the protons, and their amplitude, which is actually the percentage contribution to the whole wave function. So this says if we have our neutrons coupled to 0 plus, our protons coupled to 0 plus, that is 81% of the wave function. Okay, and that's not unexpected. Okay, so if we think of it in terms of a seniority picture, we'd have the lowest energy configurations would be where our protons are all independently coupled to angular momentum 0, our neutrons are independently coupled to angular momentum 0, and sticking those two configurations together to get a 0 plus should be a large part of the wave function. And it turns out that that is actually 81% of the wave function. Okay, so that's fine. What we do then is decompose this lot. So we decompose the case of having our total angular momentum of neutrons to 0 and protons to 0 in terms of the individual partitions that contribute to that configuration. So if we look at the big bit here, because this is probably most interesting, what this says is if we have our B partition number 3, that's 67% of the wave function. So B is protons. And if we look back to our partitions, partition number 3 for protons has 2 protons in d5 halves. Okay, so this line says here that 67% of the time we have 2 protons in d5 halves. Okay, that's all that's saying. And specifically 2 protons in d5 halves where their angular momentum is coupled to 0. And it's not surprising that this is a big percentage of the whole wave function, because that's what we'd expect in the simplest independent particle model. Seniority says we'd pair those 2 protons to 0, and they'd be in d5 halves rather than the other states, because that's the lowest energy single particle state. So what we then do is decompose the neutrons. So given that we have our protons in partition number 3 and their angular momentum coupled to 0, and our neutrons are also angular momentum coupled to 0, which partitions are the neutrons in? Okay, so we then subdivide this further. So this 67% gets spread over all the different neutron partitions that are listed here. Okay, and you see that the biggest one is this one down here. So partition number 12 has 49% of the whole wave function. So this is saying that half the whole wave function is where we have our neutrons in partition 12 coupled to angular momentum 0, our protons in partition 3 coupled to angular momentum 0, and that's half the whole wave function. Okay, so if we look back, partition number 12 for the neutrons is 6 neutrons in d5 halves and 2 neutrons in s a half. Okay, so again, this is what you'd expect in an independent particle model sort of picture to be the lowest energy state. The d5 halves is full, and also s a half is full, and so each independently they'll all be seniority 0, all coupled to 0, and our protons in just sat in d5 halves. And these will be the lowest energy states because the single particle energies are ordered that way. Yeah, okay, so this large component of the wave function is maybe not unexpected, right? We'd expect that simplest component to be there. And we'd expect it to be large, probably, in this case. But it's only half, okay? So there is a lot of strength distributed in other places. So the next biggest configuration is this number 3, okay? So this is saying that 9.5% of the time we've got our protons in partition 3 coupled to 0, and our neutrons in partition 3 coupled to 0 also. Okay, and so partition 3 for neutrons is this one here. So this is again 6 particles in d5 halves, and we've just excited those. Well, we've moved those 2 neutrons from s a half in partition 12 up to d3 halves. Okay, and again we might expect this to be a relatively low energy configuration because we can these guys will be seniority 0. They'll all be coupled to angular momentum 0, and it's a slightly smaller percentage of the wave function because these d3 halves neutrons are at a higher excitation. So this gives a lot of detail about the wave functions that you've calculated. And this is all just for the specific case where you have all your protons coupled to 0 and all your neutrons coupled to 0. It's possible, this is a sort of seniority 0 configuration. It's also possible that you could couple your protons to 2 and your neutrons to 2, and then thereby couple the 2 angular momentum vectors, which are each 2 to 0, to get your 0 for the neon 26 for the full for the full state. And this actually contributes at sort of 16%, which is not an insubstantial contribution to the wave function. But then what happens is you have a decomposition of this 16% into all the different sorts of all the different partitions that contribute. So again, we've got B partition here. So this is the proton configuration number 2, contributes at 1.5%, and then it's decomposed in terms of all the neutron configurations and so on. So these LPE files are a bit intimidating at first because it looks like a whole bunch of numbers. And they do get more complicated for non-zero spin states. So for a 0 plus state, as we've got in neon 26, it's relatively simple because there's only, you must have that your angular momentum of your neutrons is equal to the angular momentum of your protons, because they've got to point in opposite directions to give you a total angular momentum of 0 plus. But if you had a 2 plus state, say, there are multiple ways that you could get a 2 plus in terms of the angular momentum couplings of just protons and neutrons. Okay, so you could have all the angular momentum of the protons or all the angular momentum of the neutrons, or you could have something more complicated where one is angular momentum 4 and one is 2. So these files do get a bit complicated, but I think if you sit down and just go through them line by line, it's reasonably obvious what it's telling you about the wave function. Okay, so what we can do then is go on and calculate spectroscopic factors, and this is what Jeff was talking about this morning. The idea is that we have a neon 26, and we're saying what is the parentage of states of fluorine 25 plus one particular neutron in the ground state of neon 26. What's the parentage of that sort of state in neon 26? So if we take a proton out of neon 26 is angular momentum 0, and we've got to satisfy angular momentum coupling rules according to this sort of Clebsch-Gordan coefficient here. So we've got to be able to, if this is 0 here on the right-hand side, the angular momentum of the final state that we populate must be the same as the angular momentum of the proton that we remove. Okay, which means that we can populate by removing s a half plus states in fluorine 25. D3 halves, we can populate 3 halves plus states, and D5 halves, we can populate 5 halves plus states. And again, so this is the sort of shell model definition of the spectroscopic factor. On the left, we've got this neon 26 wave function, which is A body, and on the right, we have our fluorine 25 function, wave function, which is A minus 1, and we're adding to that a nucleon in a particular state K, which is J. And that's what we're defining as a spectroscopic factor. And doing the calculations is relatively easy. Once you've calculated the levels for neon 26 and the levels for fluorine 25, you can just run another calculation to overlap the two, essentially. And you tell it what sort of overlap you want to do, and it'll calculate the spectroscopic factors and spit out some results for you. And here's the results, the sort of results that you'll get for a spectroscopic factor. So these come out in files that end in .lsf. And again, this is quite complicated. Most of this is just specifying what the initial and final states are. So this first block here is all to do with half plus states in fluorine 25, and we're overlapping those with 0 plus states in or specifically the first 0 plus state in Neon 26. So this number indicates which excited state that you're talking about in which state. So we've overlapped just the ground state of Neon 26, which is 0 plus, and the first one, with all the different excited states that we calculated in fluorine 25. So they're all half plus, but they run from 1 to 10. And then this column here gives you what the spectroscopic factor is. And despite the fact that this is a PN code, so our protons and neutrons treated entirely separately, so there's no concept of isospin in these sorts of calculations. The notation for the spectroscopic factor is this c squared s, and this c squared is at least in an isospin formalism an isospin Clebsch-Gordan. Okay, so you don't need to worry about that for these calculations, but if you end up doing calculations with Oxbash or an isospin code, you need to be aware that you may, in those calculations at least, put in an isospin Clebsch-Gordan to make them agree, well, so that you can compare to experiment, essentially. Okay, and so there's some other information here on the excitation of the states, and this c squared s times the difference of the excitation, so you can sort of work out where the effective sort of single particle energies are for the states, but we don't worry about that too much. And so this file also contains information for the 3 halves plus states and their spectroscopic factors, which are rather small, and that's just a reflection of the fact that the occupancy in Neon 26 for these for the D3 halves is quite small, and for the 5 halves plus states and the 5 halves plus spectroscopic factor for the ground state of fluorine 25 is quite large. It's 1.56. Okay, and so what this is just saying is that, well, I mean this isn't unexpected because the occupancy of that 5 halves plus in Neon 26 ground state is large. Okay, so we might expect the spectroscopic factors coming from that to 5 halves plus states to be quite large. And so Jeff mentioned this morning that if you sum the spectroscopic factors over all the different final states, you'll come to the occupancy of a state. And so in some sense, once you sum these up, you have a measure of the occupancy of a particular orbital in the initial state. And you'll see that you have the same thing here, despite the fact that these are very complicated mixed configurations. If you sum each of the single particle orbits over all the different final states in fluorine 25, for S a half you get 0.25, for D3 halves you get about 0.13, and for D5 halves you get about 0.16. Okay. Now summed over all these, the total is 1.98, which is almost 2. Okay. So the reason that's not quite 2 is because there are other higher excitation states that have this remaining 1.5. No, not even 1.5%, 0.75% of the spectroscopic strength, and they just haven't been calculated in the calculation. So the calculation only runs up to 10 final states. But the point is that you have these numbers 0.25, 0.12, and 0.16. And if we look back to the LPE file for the ground state of Neon 26, you see up here where the average numbers of protons in each of the single particle states was given. And for the D3 halves, we've got about 0.13. For the D5 halves, you've got about 0.16. And for the S half, we've got about 0.15. Okay, so in the same sense that in the single particle model, the spectroscopic factor summed over the final states adds up to the occupancy, you get the same thing in the shell model. But despite the fact that the configurations are mixed and they're much more complicated, they reflect essentially the occupancies of the orbitals in the initial state. So these numbers here match essentially these summed spectroscopic factors that you see here, here, and here. Okay, so that's oh no, there's another example. Okay, so this is an example for calcium isotopes, and I suspect this is maybe an exercise this afternoon to calculate the spectroscopic factors using coefficients of fractional parentage. So Jeff showed these earlier. So the coefficient of fractional parentage is an analytic way of saying if we have n nucleons and they're coupled to angular momentum, in this case n nucleons coupled to angular momentum 0, if we take one of those nucleons out and say we've got n minus 1 nucleons coupled to J, coupled to another nucleon and total coupled to 0, what the appropriate parentage coefficient for this configuration in this initial configuration is. So these are related to spectroscopic factors, as Jeff was discussing this morning, and you have a different expression for an even value of n and an odd value of n. What you can do is calculate using a shell model the spectroscopic factors along the calcium isotopic chain. So if we start from calcium-48 and remove a neutron, go to calcium-47. From calcium-47 we can go to calcium-46 and calculate in each case the spectroscopic factors for the ground state to ground state transition, and then compare these what we expect from effectively a single particle, independent particle model estimate using a coefficient of fractional parentage. And what you see is there's this very dramatic staggering for very good reasons between the odd, the even and the odd initial states. But I think you'll go into that this afternoon a little bit more. The point that I want to make here is that actually the coefficients of fractional parentage agree very well with the shell model spectroscopic factors that are calculated, and these calculations were done in a full FP space. So the red line is the shell model, and that's calculating the full FP space, allowing mixing between F7 halves, P3 halves, F5 halves, and P1 half. And you see, certainly in the trend at least, there's really very, very good agreement. And even in the absolute values, they're almost identical, actually. You see there's a slight reduction for cases where the initial state is even. And that's just because you've got essentially mixing into the other single particle orbits, which is reducing the occupancy of the F7 halves. The fact that you don't get this for the odd cases is probably that the odd cases you have to have your unpaired nucleon has to be in the F7 halves, right? Because the ground state of your ground state of calcium-45, say, it is 7 halves minus, right? So you've got to have that unpaired nucleon in the F7 halves. And then you can sort of do what you like with the rest of them. They can mix with the FP shell as much as you like. But because that unpaired nucleon is F7 halves, to get to the ground state in the residue that you're interested in, you've got to remove that one. Okay, and so that's, I guess, why these are not reduced in the same way that the even ones are. But in general, there's really good agreement, and that's in some ways that's just telling you that you can do a very complicated FP shell model calculation involving the whole FP space. But basically, most of the wave function in these calcium isotopes, at least, is constrained basically to the F7 half shell. That's just because there's a big gap between F7 halves and the states above. So those are the lowest energy configurations, and that's what's borne out in the wave functions when you look at them. So in cases like this, these sort of CFP estimates for spectroscopic factors give you a really nice, genuinely quantitative handle on what you expect to happen. And yeah, that's verified by the more complicated calculations. Okay, so this is a sort of, I want to give a practical guide to bits and pieces in the shell model. Okay, so you may hear lots of, I don't know who's done shell model calculations before, maybe none of you have, but at some point in the future you almost certainly might have to. So it's useful to have an idea of what we mean when we're talking about model spaces, and then truncating those model spaces and the different way you can truncate them, and the way interactions are constructed, and what model spaces the interactions are constructed for. So this is just sort of a series of tips, really, I suppose. So calculations in an infinite space are not possible. We'd love to be able to do a calculation that involves every possible single particle orbit you could conceive of and mixing them all together, and maybe that will give us a fantastic description of whatever nucleus that we're interested in. But in general, it's not possible. So the larger the dimensions of your space, the bigger that diagonalization, and the longer it'll take. So in general, you need to truncate your model space, and that usually involves two truncations. So you say that we have a certain core. In our SD shell, we say our core is oxygen 16. So we say the states below oxygen 16 are closed and they don't interact with the states above, aside from maybe through the sort of central potential part. But it's closed. So oxygen 16 is closed, and we just worry about the valence nucleons on top. But in addition, effectively, we also truncate at the top of the model space. So in the SD shell, the top is calcium-40. We say that F7 halves and states above play no role in the model space. Okay, so by definition, when you're doing a shell model calculation, your model space is going to be truncated. Generally speaking, larger model spaces tend to lead to improved, well, ideally that you want to use the largest model space you can, okay? And the best calculation will perhaps use the largest model space, but obviously the computation time is going to increase as the model space size increases. And you need to be quite careful if you're just using a shell model calculation, you need to be careful that the interaction that you're using is really appropriate for the model space, and that depends on how the interaction has been defined, and if it's been, I mean, often I'll say something about where interactions come from, but often interactions are fit to particular states in a particular model space, and how they're fit and what truncations they're fit with will sort of determine which spaces you can genuinely, reliably use with a particular interaction. And often these empirical interactions are better determined for smaller model spaces, because if you're determining an interaction by fitting two-body matrix elements, then they might be better determined if there's less of them, effectively. Okay, so this is the sort of field guide to the sorts of model spaces that are available. The shell model has been applied to lots and lots of different bits of the nuclear chart near and around closed shells. So right down the bottom here we have the P shell, which goes from, which has a helium-4 core and up to oxygen 16, just P1 half and P3 halves. And moving up, we have the SD shell, which I've talked about already today, which is everything between oxygen 16 and calcium 40. Further up still, there's the FP shell, which is where I did the calculations for those calcium isotopes running along this bottom edge, effectively. And then within that, you could truncate that to have just the F7 halves state, which is what effectively the independent particle model CFPs would give you for spectroscopic factors. And then there are bigger model spaces, so there's a space that SPS DPF. So in principle, that runs from 0, so effectively that has no truncation at the bottom, right up to nickel 56. And I'll talk about a particular interaction in this space and how it's derived and how you can actually use it. But there are, when you have interactions that cover different major shells, often they're divided into different major shell parts, and there are different parts of the interaction for different shells, but I'll talk about that in a second. And then you can keep going up. There's this JJ44PN, which has a nickel 56 core and then goes up to tin 100. And then there's various others up here that have these JJ names based on the major shells that they are covering. And these numbers in brackets are the numbers of interactions that are available with NuShellX for doing calculations in these model spaces. So you can see, particularly in light nuclei, there's lots of interactions on the market. And really, well, it's usually good to do calculations with several different interactions so you can compare the results, but also you do need to tend to go back to the original papers and look at how an interaction was derived and what it's actually designed to do, because they're not necessarily always designed to do the same thing. I mean, interactions in a space like this could be appropriate for near lead-208, or they could be appropriate for right at the other end. Okay, so and it depends on what the original objective was when the interaction was produced. So there are lots of different model spaces, and there's this file label.dat that you'll see in the tutorial that contains a list of everything that's available for doing calculations. So what does an interaction, what does a model space file actually look like? So this is the model space file for this SPS DPF. So this covers everything from nothing, 0 effectively, right up to the top of the FP shell. And this is actually what's read by NuShellX to define what the model space is. And it's not that you'll ever actually need to look at these files, really. So more often than not, you can use a stock interaction and a stock space. But it's useful to know what actually goes into the calculation to define the model space effectively, right? So this starts with a name, and then this starts with a label that says whether the interaction is in isospin format or PN format. Okay, so because of the heritage of NuShellX, it's come from Oxbash. Oxbash was an isospin code. So its interactions are all in isospin format, and that just means that they've also got an isospin label for each matrix element. And NuShellX is a pure PN format code, treating the protons and neutrons separately. There's relatively simple relations to convert between matrix elements in isospin format and PN format. Okay, so you don't need to worry about it. Just that this means that when the code reads it, it will interpret the interaction in a particular way, and then it will convert it to a PN format interaction. So you don't need to worry about that particularly. This just defines what the core of the model space is. In this case, it's 0. And then there's these definitions of the subshells, the orbits that are involved in the calculation. So this gives you the number of subshells. In this case, there are 10. And those are listed here. So we ignore this line for a second. So those orbits are the 0s1/2, 0p3/2, 0p1/2, 0d5/2, 0d3/2, 1s1/2, 0f7/2, 0f5/2, 1p3/2, and 1p1/2. So I'm saying ones, and I'm saying zeros rather than ones. So this these letters indicate the principal quantum number, and I often say 0 instead of 1 because so 0 is if it's got the principal quantum number of 1, then 0 will be the number of nodes in the wave function. But anyway, that doesn't matter too much really. The point is that these indicate the principal quantum number, the orbital angular momentum, and the total spin of each of the single particle states that are involved in the calculation. And you can see that this lot covers what you'd expect for everything from 0 all the way up to the top of the FP space. This line here in between the two defines the number of major shells. So particular sorts of truncations, not in NuShellX as it happens, but in other codes you can truncate on the basis of excitations between major shells, and we'll come on to that shortly. All this says is that this model space covers 4 major shells. The first major shell has 1 orbit in it, which is the s1/2. The second has 2, which is the p-wave states here. The third has 3, which is these 3 here. And the fourth has 4, which is the FP shell up at the top. So these are the sorts of things that go into defining what a model space is. As I say, you won't ever really need to edit these files, but it's good to have an appreciation of what goes into it and what's required to define the calculation that you want to do. The residual interactions, as I said earlier, if you've got, you need to calculate matrix elements between complicated states of however many number of particles you're calculating for with your residual interaction. And the point is that you can reduce these to just 2-body matrix elements between pairs of 2 particles in different states. And so specifying this residual interaction just consists of defining a set of single particle energies that are related to the central potential part, basically, and a set of 2-body matrix elements. And each interaction is designed for a particular space. So a particular space will require a particular set of 2-body matrix elements because it covers a certain range of orbits, and you need all the 2-body matrix elements for all the different pairs of orbits that go into that space. So they may only be appropriate or feasible for a part of that space. So as I say, if it's defined for one extreme end of a very big space, then it's going to be appropriate for that end, but it might not work right at the other end because the single particle energies may change and the 2-body matrix elements may have changed. And in model spaces crossing major shells, the interaction may only really work for certain sorts of truncations, and I'll say something about that in a second. Okay, so the origins of interactions, as I say, they're defined by for a particular model space, and they consist of single particle energies and 2-body matrix elements. So the single particle energies are often taken from experiments. So if we think of our SD shell space, the single particle energies, which is related to that central part of the interaction, can just be taken from having 1 particle outside our core. So if you think of oxygen 17, if oxygen 16 is a good core, that 1 valence neutron has nothing to interact with in terms of other nucleons outside the core. Okay, so if you look at the excitation spectrum of the low levels in oxygen 17, that can help you define what these single particle energies should be for an ST shell space. Two-body matrix elements are a bit more complicated, so they're either usually, well, so they can be sort of empirical, either calculated using a phenomenological potential, so you somehow parameterize your two-body interaction, actually physically calculate the matrix elements between different pairs of two-particle states, or they could be fitted. So you could say, okay, we've got our ST shell space and we're going to take these states and these nuclei, and maybe you take 20, 30, 50 states. You do a whole load of shell model calculations and you adjust the two-body matrix elements to fit the excitations of those states. Or it's somehow maybe a combination of the two, so you might start with a two-body matrix elements from a phenomenological potential and then adjust particular matrix elements to improve agreement with experiment. And there's some question whether if you're fitting them in this way, whether it's still predictive to do a shell model calculation. But it sort of depends which nuclei you're fitting and how you're generating the interaction in that way. Or there are sort of more realistic methods where the two-body matrix elements are calculated using a free nucleon-nucleon interaction. But again, they can be used as a starting point for some degree of fitting to adjust to get better agreement with experiment. And as I say, often a realistic guess is used as best guess to start with. So this is what an interaction looks like. Again, you're not going to need to edit these, but it might be useful to look at them to know what goes on inside and what's actually required. So there's some header information here, and the ordering of the single particle states is usually given. So like I said, this is for the SD shell and the USD interaction. So we've got D3 halves, D5 halves, and S a half, which is an ordering that was consistent with what we showed earlier for the level files. And this is clipped off the edge, unfortunately. But what you have here are, the first line gives you, this tells you the number of two-body matrix elements, and these four numbers are the single particle energies for the interaction. And then what you have are 4 columns. I think the first one is cut off here. 4 columns indicating the indices of nucleons in particular states. So you have O1, O2, O3, and O4, which are the 2 pairs of nucleons for the two-body matrix element. The value of the isospin, which is here, and the total angular momentum coupling of the 2 nucleons, and the value of the matrix element. Okay, and this is what's coming from your phenomenological fit, or from your potential, or from a realistic calculation. Yeah. So the slide is slightly cut. So the first one is sort of over here. Yeah, no, but in here there is another column. And you see, so the first lot of what have we got here? 0, 1, 2, 3. So all of these here. So in this case, these are all 1. I could probably just show you actually, but they're not. So yeah. Okay, so you can see it there. So the first 4 are 1s, and you could tell they were fuzz. So all of these are 1. So this all means that these are matrix elements for 2 nucleons and D3 halves. So 4 nucleons and D3 halves, but matrix element between pairs of nucleons and D3 halves. And you can tell that it was going to be D3 halves from the angular momentum couplings available. So you can couple 2 nucleons and D3 halves to 0, 1, 2, or 3. If they're like nucleons, then you can only get to 0 and 2, so the isospins there are 1. And if they're unlike nucleons, you can couple them to 1 or 3, and the isospins there are 0. Okay. So then you have matrix elements for all the different allowed angular momentum and isospin couplings for those 2 pairs of nucleons. That's not good. Right, let's try that again. This one? Yeah. Okay. And so this file goes on. There's 63 different matrix elements that you can have that are just coming from different combinations of pairs of particles in the 2 orbits, and they're all allowed, all they're allowed angular momentum couplings. Okay, so that's effectively what a residual interaction is when it actually goes into a calculation. It's just a list of two-body matrix elements that have been calculated in some way. Okay, so model space truncation. So calculations in full space are usually too computationally, well, it depends what you mean by full space, but I mean, you have to truncate the model space somehow. But it's key that the truncation that you do has got to be appropriate for the interaction that you're using. So in the SD shell space that we'll use later, then there's no need to truncate. So it's a small enough space that you can do a calculation in the full space without too much trouble. Different sorts of codes will allow different sorts of truncations. So because new shell X is a PN code, it's treating the protons and neutrons entirely separately. So you can only truncate protons and neutrons independently. There's no way of truncating the sum of excitations of protons and neutrons, say. So I'll come on to that in a second. Yeah, so you cannot restrict the total numbers of protons and neutrons in a given orbit. So you couldn't restrict, say, the total numbers of protons in D5 halves. The total numbers of protons and neutrons in D5 halves. Only the protons and neutrons independently. And that proves some, gives you some complications when you're looking at particular interactions. Okay, so here's an idea of a sort of truncation that you might want to do. If we imagine an SDFP shell, so we've got here all the orbits, all the states in the SD shell and all the states in the PF shell. Doing a calculation that's full space wouldn't be possible. There'd just be too many partitions, too many ways of putting the nucleons in these states, too many ways of coupling them, and too big a matrix to diagonalize. So say you wanted to do calculations that were sort of southeast of calcium-40 on the nuclide chart. So you want to shut off the proton excitations into the FP shell, and then you could treat, say, calcium-40, N equals 20 as a core for the neutrons. Okay, so you would then maybe allow your protons to be freely distributed across the SD shell, and your neutrons to be freely moving around the FP shell. So this is a sort of truncation you can do in new shell X, just blocking off single particle orbits or limiting the number in particular single protons or neutrons. And if you were looking at this on the nuclide chart, you can imagine over here blocking off the so this is just the definition of, where are we up to here? This is nickel 56. Okay, so this is blocking off the protons above N equals 28, say, I think. And here are the neutron states, proton states. And then you could block off the protons above F7 halves, okay. And there are neutrons, and we could block off below the SD shell for neutrons. So what you're left with is neutrons in the F7 in the F7 halves effectively here. Oh no, sorry, neutrons in the full FP shell and protons below in the SD shell. So you could do other sorts of truncations if you wanted to. You could block off protons and neutrons symmetrically. You could say, we're going to say that the proton D5 halves is full and the neutron D5 halves is full, but we're going to block off the higher FP shell. So we're not going to say that, we're going to say that protons and neutrons can't be in the F5 halves and the P1 half. And this is the sort of truncation you can do by affecting individual proton or neutron single particle states. So the question is, though, is the interaction that you're using actually designed for that space? So there is another sort of truncation that was available in Oxbash at least, and isospin shell model codes, where you actually you can limit the number of nucleons you excite above a major cell gap. So if we were to think of our SD shell and our FP shell again, and say we have A nucleons in an isospin way, we've got A nucleons. We don't know if they're protons or neutrons necessarily, but there are A of them below the SD shell. So this is something below calcium-40. We can say that this is called a sort of 0H bar omega excitation. So all our nucleons are below this major shell gap. But we could conceive of having a different configuration, for example, where we excite two nucleons from below the shell gap to above the shell gap and put them in F7 half, say, or anywhere in the FP shell. And this is called a sort of 2H bar omega excitation. So you've taken two particles from below a shell gap and moved them above a shell gap. But unfortunately, this is the sort of thing that you can't do with new shell X, because this relies on the fact that you've got protons and neutrons being treated on a similar basis. Okay, so when I say 2H bar omega exciting two nucleons, these could be protons and neutrons. They could both be neutrons, or they could both be protons. And depending on what sort of thing you're calculating, maybe you'd expect them to be neutrons, and maybe you'd expect them to be protons. But this sort of truncation is kind of agnostic with respect to the sort of nucleons that they are. But because new shell X is treating those protons and neutrons separately, there's no way to do this sort of truncation. No way to truncate both protons and neutrons at the same time. Okay, so just to give an idea of where interactions actually come from and how they're constructed. So there's an interaction that's rather popular in the sort of PSD shell. It's called the there's two interactions that were coming from the same paper, WBP and WBT, and they were just fitted to slightly different things. But what we're doing is in the PS, so we have a P shell down here and then the SD shell up here. What are we going to say next? So we've got 0P down here and the SD shell. And our interaction is going to consist of a bit that tells you the residual interactions between nucleons in the P shell and a bit that consists of residual interactions that are between nucleons in the SD shell. But there are also going to be interactions between nucleons that are in P and nucleons that are in the SD. Okay, so there's going to be some cross-shell interaction between the two bits of the space. So that you can have interactions in between 0P neutrons and SD shell protons, or interactions between anything in between, basically. And the way this interaction was derived is that what was taken was the USD shell interaction, which already existed for the SD shell space, so residual interactions purely for the SD shell space, and a residual interaction was taken for, I believe, for the P shell part, that again already existed and was well derived for the P shell. And then the cross shell part, the interaction between P shell and SD shell, was fit to a series of states that were in this region. Okay, so what were defined were 86, the 0P shell bit was refit, and 86 states in the P shell were used to fit the two-body matrix elements. There were 148 states, which they said were likely to be one particle excitations across the shell gap. So I guess mostly, particular states that they could identify, saying this is probably a simple single particle excitation across the shell gap, and the energy of that state to constrain the cross-shell interaction, and 10 states that were thought to be two particle excitations across the shell gap, and they were also fit. So all these states were used to fit the cross-shell part of the interaction, but the point is that that fitting procedure relies on the nature of these states being a certain character. Okay, so it's saying that these one particle states are 1H bar omega excitations across the shell gap, and this could be a proton or a neutron, or it could be, it's either a proton or a neutron excitation across the shell gap. But that truncation has been used, and it's been in mind when the fitting has actually been done. Okay, so it's important to know that when you're using this sort of interaction, it's been fit in a particular way using particular sorts of truncations. And the other thing is that there's no mixing allowed of 0 and 2H bar omega states. So if you have a pure 0P configuration where all your nucleons are in the P shell, that sort of state was not allowed to mix with configurations where there are two extra nucleons in the SD shell. And those mixed configurations were not included in the interaction. So doing a calculation where those configurations are allowed to mix is really going beyond what was actually originally intended for the interaction. So you need to be quite careful when you're doing a calculation what's gone into defining the interaction and how it should be used and how it was intended to be used and what it was fit to, basically. Okay, so just a very brief last bit on, we got So on the history, so Oxpash was originally designed back in the 70s and evolved over a reasonably long period. And Bill Ray, who was at Oxford, he's now retired, I think, rewrote most of Oxpash in a more modern way. And that was a code called GNU Shell, which subsequently gained a sort of PN version, which was GNU Shell X. And Alex Brown at MSU has written a series of wrapper codes that allow you, help you set up the calculations and allow you to do additional calculations with the results. It's very powerful for structure calculations. It's very flexible, but it's very easy to do things that are not sensible, or try and run a calculation that would take 3 years to run or whatever. So you need to sort of approach it with some practical sort of ideas in mind. So for the tutorial session this afternoon, there's a tutorial written and it should be on the website, and there'll be an updated version. You've got to log on to a Windows machine to run it. So we'll put instructions up on the boards of how to access the Windows machine. And then hopefully it won't fall to pieces when everybody logs on at the same time. But we'll see. And so that will run you through a relatively simple calculation, the Neon 26 proton spectroscopic factors. And if you've got particular things that you want to try, I'm happy to help and give advice on whatever calculation that you might want to do for whatever that you're doing outside at your home institutions. So in general, you need to choose an appropriate model space, choose an interaction that are listed in this label.dat file that you'll see in the tutorial, and then decide if model space truncations are required to actually do the calculation that you want to do. Those have got to be appropriate for the interaction, and usually it's best to truncate reasonably severely. So what you could get a lot of understanding from a relatively simple calculation and then relax the truncations and see how it improves, basically. And when publishing result from a shell model calculation, it's really important to give sufficient detail that they can easily be reproduced, because I've spent quite a lot of time trying to reproduce some of these calculations and they haven't given you a very crucial bit of information that how they change the interaction or something. Okay, so yeah, this just gives a summary of the files that we've been through earlier. These LPE files contain the levels and LPT files contain the summary. And then once you've done the level calculations, you can overlap two different sets of levels to give you spectroscopic factors, say. So an A body state with an A minus one body state and this creation operator in between. And you can calculate other sorts of transitions, so you can calculate electromagnetic transitions or BFGTs for beta decay. And these subsequently, once you've calculated the overlap of the shell model wave functions, you need to process them with DENS. So DENS is a program you've already used to calculate density distributions, but you can also use it to calculate transition rates that require some kind of form for the radial wave function. But I don't think we probably won't get onto that today. Okay, so that's about it. So in the tutorial, we'll run through a sample calculation, and then if you've got things that you want to do or advice on calculations that you might be interested in, then by all means ask. That's about it. Any questions? I don't know how long it's been. Yeah.
It's still unclear about how to read the LPS file.
Which one? The spectroscopic factors or
Yes.
or the levels?
My boss.
Yeah. Okay. Well, it might be better if we just we go through it in the tutorial session. So it's a bit complicated, and it looks a bit of a mess to start with. But yeah, I think it's probably best if we sit down and do it in a tutorial session. I mean, it's once you know what you're doing, it's reasonably simple to see how it comes out. But yeah, we'll sit down and talk about it. But, well, yeah.